All right, guys. So this afternoon, we're taking a look at the continuation of this related rates problems. I would say they just get more complex. I wouldn't say that the work or the process is any different, right? We're still trying to come up with an equation that relates the two variables that we're talking about. In this instance, or most of what we've been talking about so far today, it's been volume and height of water levels rising, right? So we're going to see that again with this question. I've taken the liberty to draw the picture in advance here, just to save some time here. But um, again, it comes down. You got to be cognizant of the fact that there's multiple things going on here, and this is more realistic of the world that we live in, right? Is There's multiple things going on at any given time. So anyway, what do I mean by that? Well, here we've got this trough. It's a water trough, and it's 10 meters long. It has a cross section of an isosceles triangle that is 1 meter across at the top, and it's 50 centimeters high. Okay, the trough is being filled at a rate of 0.4 meters cubed per minute. How fast is the water level rising when the water is 40 centimeters deep? Okay, so I've just drawn the picture. Now, you guys should be aware of the fact that a trough here, this is just basically a triangular prism. And if you guys recall, the volume for a triangular prism is going to be 1/2 the base times the height times the length. Okay, and we will look like we know most of that information. The problem is, again, the same as the cone question. Okay, as this water level rises and gets higher and higher, you're going to see two things happen, right? So I'm going to draw this face on here for a second, just so it's clear what I'm talking about, right? The problem. Oops, here. I'm going to draw a nice triangle. Just so it's clear what's going on. So as this thing, here, maybe I'll use the highlighter in blue. As this thing is, if it's down here, it's increasing water level, it's filling up, filling up, filling up, filling up, filling up. You'll notice that two things are going on there as I do this. The height is changing. We're getting a delta H, right? But at the same time, much like the cone question, I'm seeing a delta W, a width. Okay, so there's both of these two things are changing at the same time. The base here, I suppose we could call the width. Width times height times length. Okay, and so these two things here are changing simultaneously. And we've seen how to deal with that. Again, what's nice about the triangular prism is we can set up a scenario where, and I'm just going to erase some stuff here just so we can use this actual diagram. I'll add the color back in here. Okay, we have a scenario much like the cone, right? We know that across the top it's 1 meter from side to side. And I also know that this thing is 0.4, sorry. Oh no, 0.5, I'm right. 0.5 meters tall, okay? Now, we have this scenario where we have this water level here. We want to know what this width is, right? And what this height is. So again, much like the last question, I suppose we could call this W naught and H naught, okay? So ultimately, our end goal here, okay, has not changed. We are interested in expressing a volume with respect to how the height is changing. Okay, this is our goal. We want to have an H variable on the right side so that I can implicitly derive and find how dH and find dH dt, basically, right? That's what I'm interested in. So how are we going to go about doing that? Well, it's of no use to me to have this W in here, right? Much like the cone question. We're going to do the exact same thing, okay? The width, why don't we find an expression where we're able to write the width with respect to the height for all heights of water level in this trough, right? So that's what we're going to do. We're going to look for an expression H naught is equal to something over something. Okay, that's what we're going to do. But it's no different than the cone question from the standpoint that we have similar triangles here. right? And so we could say, okay, well, W naught over 1, right? I'm just relating the two widths. That has to be equal to H naught over 0.5. Okay, I can do my cross multiplication work here. We can see 0.5 W naught has to equal H naught. That's not really what I'm interested in. Okay, if I were to take H naught and plug it into here with the W, now I have width on my right side. That's not what I'm interested in, okay? Not for the context of this particular question. It's not asking how the width of the water is changing, right? That's lesser of the two interesting scenarios here. It's asking for how the height is changing, okay? And so in order to get height on the right side of this equation, I have to get what W is with respect to H, okay? So I'm going to divide both sides by 0.5, right? Or 1/2, and we're going to see that W naught is going to equal 1/2 of H naught, 0.5 H naught, if I divided both sides, right? All right, so we have what W is going to equal. This is for any height inside the trough, we know what the width is, okay? That's what we've done. So we can come up here now. We're going to say 1/2 of W. We now know what W is. W is, we have the original 1/2, and then we have a 1/2 H naught times H, right? These are going to be the same, H. And that needs to be multiplied by L, not 2, geez, L. Okay, so we're going to get the volume with respect to the height is going to be 1/4 H squared L. So hopefully everybody has kind of followed along with that, with what's happened, okay? This is an important equation from the standpoint that now, if I differentiate this with respect to time, right? L is a constant. It's 10. It's not changing, right? So we could basically bring that over to here, right? We could say, okay, we could rewrite this equation to be V equals L divided by 4H squared, okay? Length is not changing with respect to time. It's fixed, right? This is always going to be 10 meters no matter what, so it's a constant. I'm not really going to derive it, right? If I derived it, I get 0. So the only thing I'm interested in here is how this height is changing. So let's implicitly derive this volume equation that we have sitting here, right? So we could say, well, dV by dt, that's going to equal L divided by 4 times 2H times the derivative of that with respect to time, dH by dt. Okay, and so I see dV by dt is going to equal 2L, or we could even call it, we could say here, just so you guys can see, the 2 is going to cancel with a 4 there, and we're going to get a 2 in the denominator, right? So we're going to see our next line would be L divided by 2 times H times dH by dt. We know all of this information now, right? If you recall. So just going through the question here, I'll highlight the key pieces of information. We know that the trough is 10 meters long. That's L. Then I know the rate at which the trough is being filled. That's 0.4. That's how the volume is changing, right? That's what we're adding. And then I know the isosceles triangle, the width doesn't matter there, that we use that to help us there. We know H. H is the water level in there, right? When the water level is 40 centimeters deep, so that's H. What is it we're looking for? We are looking for dH by dt. Okay, so let's do some isolation here. I'll try to actually, you know what? Here, let's move all this stuff over. I can move all of this. There you go. A lot of some room there. Okay, so let's do some isolation. and get dH by dt by itself. Okay, we could say, okay, well, it's 2 times dH by dt is equal to L times H dH by dt. I could divide both sides by LH, so I'd get 2 times dH by dt divided by L times H. That's going to equal what it is we're looking for. How is the height changing with respect to time? Let's plug in our numbers and find out exactly, okay? So we're going to get 2 times, what's the number for the rate? That's the red number, 0.4, divided by, what's the length of this trough? 10 times the height of the water, 0.4, which is convenient. Too convenient almost, but it's okay. Okay, the 0.4s will cancel. We will get dH by dt will equal 2 over 10, which will equal 0.2. And that will be in meters per minute. Okay, guys? Not an easy question by any means, okay? But again, I'm just trying to reiterate the fact from this morning, okay? I encourage you guys to have a look at what's going on with these questions, right? These are not easy questions from the standpoint, again, nothing in the real world is easy, right? Because there's multiple things changing at the exact same time. So the way we tackle that is to take one of the variables and write it with respect to the other one. Right? And then we are able to implicitly derive and solve for explicitly how something is changing relative to time. Okay? So anyway, that's a trough example. Quite tricky. Okay? If you've never seen that before, that's very difficult. But hopefully this video helps, and you guys will be able to tackle these trough questions and subsequently any other questions that are changing multiple variables at the same time a little bit easier. Okay? So I'll stop the video there. I'll do the hemisphere in the next video, so I'll see you there.